Welcome, Mr. Mohan. Nice to see you. Hereby, I open this academic ceremony in which Mr. Mohan will defend his academic thesis entitled Retinal Axiometry in Health and Disease, and I would like to invite him for the next 15 minutes to present his work so we can start later and discussion about the work. I would like to give you the word and looking forward to your presentation.
Thank you very much, highly esteemed Pro-Rector. I'll just start my presentation.
Yes.
Is my screen visible?
Yes, it is visible.
Yes, to us also.
Yeah. Good afternoon, everybody. I'm Dr. Ashwin Mohan, and I will be defending my thesis titled Retinal Oximetry in Health and Disease. So what is retinal oximetry? It's formed of two words. One is retina and one is oximeter. So the retina is the layer at the back of the eyeball that is light sensitive, that captures the light and converts it into electrical signals that the brain can understand. And oximeter, all of us would have heard a lot about it over the last 1 year because of Corona. So an oximeter is basically a meter that measures oxygen. So where exactly is the retina? If we cut our eyeball sideways, if we look at it from the side, then this yellow thing that we can see at the back, the yellow layer that we can see at the back is the retina. And this, as I said, absorbs the light and converts it into electrical signals that the brain can understand. So these fibers, they travel through this yellow disc that is shown by the white arrow here. So this is the optic disc, and we can see that there are red lines that are coming out of this. So what are these red lines? These are the blood vessels. Half of these are arterioles that bring oxygenated, oxygen-rich blood from the heart into the eye. And the other half are the venules that take away deoxygenated blood or the blood without oxygen towards the heart. So how exactly does this blood carry the oxygen? So here we are introduced to the term oxygen saturation. So basically, blood carries this oxygen in hemoglobin. So what is hemoglobin? Hemoglobin is like small boxes inside which oxygen is carried. So assume we have got 10 boxes, and if all these 10 boxes have oxygen, blood is 100% saturated. If only 5 boxes out of 10 have oxygen, the other 5 are empty, then blood is 50% saturated. So just consider oxygen saturation as a measure as to how much oxygen there is in the blood. Higher the saturation, higher the blood. Higher the saturation, higher the oxygen in the blood. So this is a very interesting graph. We can see two lines here. One is a red line and one is a blue line. This basically shows us how much light is absorbed by the hemoglobin at different colors of light. So the red line shows how much light is absorbed by oxygenated hemoglobin. The blue line shows how much light is absorbed by deoxygenated hemoglobin. We can see that there are certain points where the red and the blue line cross. This means that oxygenated and deoxygenated hemoglobin absorb an equal amount of light, but there are points where they are completely different. Here the absorption is totally different, and this is the basic principle where, based on this difference of brightness, we calculate how much oxygen there is in the blood. So what do we basically do? We shine two different colors of light into the eye. One color absorbs light equally for oxygenated and deoxygenated hemoglobin. At the other color, oxygenated and deoxygenated hemoglobin absorb differently. In this case, oxygenated blood, that is blood with oxygen, hardly absorbs light, whereas blood without oxygen still absorbs light. And this difference in absorption, this difference in brightness is what tells us how much oxygen there is in the blood. So this is the apparatus we use, the camera, and the black part on top basically splits the photograph into the two different colors, and these two different colors we can see on the right. The upper part, we can see that there are many vessels. This is because both oxygenated and deoxygenated blood absorb light equally. Whereas in the one down, we can only see half the vessels. The vessels with oxygenated blood are not seen because oxygenated blood does not interact much with this wavelength. And then based on the difference in brightness, the computer analyzes them and it calculates how much saturation there is, and it displays it as a map on the right. So higher the saturation, more red is the color. If it is somewhere in the middle around 50, then it will be around green. And if it is very low, then it can be blue or even purple. And then how do we get this saturation over that? So there is a method for that. What we do is we first look at the areas where the vessels cross each other or where the vessels branch, and then we mark them. Then we draw two circles, one closer to the optic disc and one slightly away. This is basically the area where the image is the sharpest. And then after that, we mark the thickest arteriole and the thickest venule in each quadrant. That is in each quarter part of the eye. And then we get the saturations. So what did we try to do in the thesis? Well, first we wanted to see what happens in normal eyes. Then we wanted to see if that complex method that I showed you can be automated, because a different person can mark a different vessel and the values can be different. So we wanted to avoid that subjectivity. So we wanted to see if we can automate it. Then we wanted to look at the impact of the RNFL. So what is the RNFL? Consider this as a covering for the retina. It is a topmost layer of the retina. And then impact of the imaging protocol, that is, we wanted to see whether the angle of the camera can have any difference. And we then wanted to see how oximetry, after we have seen what is normal, we wanted to see how it is a disease. We wanted to see whether there are any pitfalls, any drawbacks of this problem. And then we wanted to do modeling. What is modeling? So when we are making our house, we generally make a drawing on our computers before that. The architects would probably show it to us. So modeling is something very similar to that. We make a drawing of the retina to understand how the light would travel within that. We defined what is normal, three important numbers, 90, 57, and 33. Like we said, 90 comes from the heart, 57 goes back to the heart. So we know that 90 minus 57, 33 is what the eye has absorbed. And that is the AVSD, or the arteriovenous saturation difference. Now, this 90, 57, and 33 is the average for the entire eye. But if we look at this more closely, I had spoken about quadrants earlier. We can see now on the upper right side, if we see 94, 60, and 34. And on the lower left, we see 86, 51, and 35. We can see there's a lot of difference between these numbers. And we did see difference in quadrants. Generally, the upper right, that is the superonasal in this right eye, would generally have higher saturations as compared to the inferotemporal. Then we tried to automate this. So what we did was we made the software take out all the colored pixels, all the colored parts of that image. And then we asked it to tell us what the saturation was, and the number of pixels, that is the number of dots having a particular saturation, we counted how many dots were there. That is called a frequency. And these tall buildings, these bars basically represent how many pixels had that particular saturation. And so this is called a bar graph. And then we tried to find which were the two saturations which had the highest frequency, or which occurred the most. And this is called a bimodal graph. And these two frequencies told us what the arteriolar, that is what comes from the heart, and what the venous is, that is goes towards the heart. There were many advantages of this. One is this was same whoever did it, because it was an automatic method. Two is because it was automatic, it was very easy. Three is it because it showed frequencies, averages would not affect it. And four is we did not have to manually choose arterioles and venules. So this gave us a very easy thing. But then what we also saw was, we saw that when the background was brighter, the saturations were lower. Like you can see this first arrow here, the background is bright. Now the next arrow is in an area where the background is a little dark. And what we saw was in areas of darker backgrounds, the saturations were higher, like you can see on the image on the right. And this observation really interested us. So then we went on and we looked at the RNFL thickness, and we found that wherever the RNFL was thicker, the saturations were lower. Then we tried to see with different angles of the camera, and we found that when we took it straight, we found differences in the quadrants. But when we looked at the sides, when we imaged each quadrant individually, those differences disappeared. And this gave us very interesting insights. We felt again it was the RNFL which was the main reason for this. Then we try to see what happens in disease. Amblyopia, as many of you might have seen, is a lazy eye. So this eye sees less as compared to normal. But then, I mean, so the one on the right is the amblyopic eye, and the one on the left is a normal child with a normal eye. And when we examine the retina, when we look at the retina, when the patient is with us, we cannot find any problem. So we wanted to see if oximetry can give us a problem. And what we saw was there was a slight difference from that same child's other eye, but not that much from normal. Then we wanted to see how a few children genetically from birth have low vision. So we wanted to see how this was different in them. And what we found was that, first of all, there were lesser vessels and the saturations were very high. Then we wanted to see when a particular vein or an artery, if it is blocked, or if the capillary bed is blocked, like in sugar, there is a lot of sugar in the body. The sugar goes and sits in the vessels. And how does that change? So even in that, we found that the saturations were increased, except for when the arterioles were blocked. So there were many things. Let us summarize the entire thing in this table. So what we can see is in the CRAO, that is the central retinal artery occlusion, only in that we see that the saturations decrease. In the rest of them, they have either increased or they are comparable. This is a very interesting observation because we can see that the arteriolar saturations in 5 out of 8 diseases was increased. And this didn't make sense to us because the only place where oxygen enters the body, as we know, is in the lungs. In the eyes, a disease should not ideally increase the oxygen, but that is what we saw. So we decided to investigate further, and we tried to see what are the problems that can be there. So if we see this image on the upper left side, we are looking at the exact same vessel area in the two images, but because the background is a little lighter in one of them, the saturations were lower. And this again did not make sense to us because it is the exact same vessel segment. On the image on the upper right side, what we can see is we can see many of these tiny purple lines. And basically, these are areas where there are no vessels. It is actually an area of a pigment problem. But still, the software would identify it as vessels and give us wrong values. And then we can see on the lower right side, we see two photographs. Both the photographs have been taken at the same time. Only one photograph is blurry, is less focused. And even that creates a problem in the oxygen measurement. So the photo that we take has to be very well focused. So we realized that there are a lot of problems with this. So a few of the main problems were that the saturations went above 100%. The arteriolar saturations were very different within the same eye, which was not explained. They were significantly increased in disease states, again, which was not explained. And we also found an increase in the saturation difference. Now, generally, when there is a disease, we have a loss of tissue, like with age or with retinitis pigmentosa or with glaucoma. In these, the retinal tissue decreases. So when there is less tissue, there would be less oxygen use. And when there is less oxygen use, there should be less saturation difference, but we found an increased difference, which again did not make sense to us. So we went on to do the modeling. Basically, what we did was we tried to adjust, we tried to put the vessel, we tried to put some tissues on the side of it and on top of it, and we tried to analyze how the light that is traveling through it can change, or how the measured intensity of light can be different. And we had some very interesting findings where we felt that we had identified how these tissues can alter the light, but we have still not been able to find a complete correction or a solution to the problems that we mentioned before. So we did discover significant artifacts. Through our findings, what we say is that the study should be longitudinal and not cross-sectional. What this means is that a single visit, we cannot with proper conviction say what the patient has with proper certainty. But if the same eye of the patient is probably compared to itself a few days before, we might be able to have something. And we very strongly feel that we need more equations, or we need more independent variables to address these unknowns, and probably more than two wavelengths, probably 3 or 4 different colors of light may solve the problem. Thank you.
Thank you very much, Mr. Mohan, for your accurate presentation, very well illustrated. And we are very interested now to start a discussion about this and about all the chapters in your thesis. So the opposition will be opened by Professor Mess. Professor Mess was the chair of your assessment committee, and he is appointed as professor in clinical neurophysiology at our hospital. And I'd like to give him the first word.
Thank you. Well, dear candidate, thanks a lot for your presentation. And well, first of all, of course, my congratulations to you and the whole team of supervisors. With this, I really have to say this is quite substantial thesis you have written. And when I scrolled through it, there were two moments of flashbacks. So when I was pretty young, I read everything of Hermann Hesse, and I think I read the most important books of Ayn Rand too. So obviously we have some common interests here. And this, of course, holds true for the thesis too. And since the retina in the end is a part of the central nervous system, and I'm a neurologist. So I am also very interested in the blood supply of the brain, and I was very curious about your findings. And in the end, I was completely surprised. So let's talk about that, why I was so surprised. We start very simple with the normal values you found. And that is page 23 and page 24. Okay. So for the arteries, the saturation was 95%. This comes as no surprise. Standard deviation 6.6. The veins 56.9. Standard deviation 6.3. Which, well, so for the arteries, I understand not so interesting. Veins maybe more interesting. Which value for the venous oxygenation would you then regard as pathologic? Looking at the mean and the standard deviation in a given measurement, what would be a pathological value?
Thank you very much, highly esteemed opponent, for your comments. So, like you said, it's not very important for the arterioles, for the venules, and with such a large standard deviation, if we say that the average is 57 with a standard deviation of 6, you're looking at a normal range of anywhere between 45 to 70, and that is a very large range.
Exactly.
And with
that is the right answer. Thank you. This is perfectly reflected in the graph on page 23. There is just one subject above 70%. So this is completely true. Did you find any patient in during your whole study with a pathological eye, because this is normal persons, who was on top of this 70%?
Yes, there were eyes, especially in the diabetic group, especially in the severe NPDR group. And we also found it in eyes with retinitis pigmentosa. So in those subjects, the arteriolar saturations would be 120, 130, and the venous saturations would be 80, 85. Even in glaucoma subjects, there would be a few with very high venous saturations. Also,
actually, this surprises me a little bit. When I look to the table on page 105, chapter 7, which is on retinitis pigmentosa, there I see the venous saturation is 59.1, and I think in brackets, is that the standard deviation, or is that the range, or what is that?
That is the 95% confidence interval.
Okay, so that is quite a lot of patients, and then you are really very well below the 70%. So I think you already wanted to say it, but I interrupted you. This range is very large, and it is very unlikely that you will find a patient with a saturation higher than 70% in the veins. So it's very difficult to use this in the individual patient. But I want to go on the values you found, because the machine you use is from Iceland, and it comes as no surprise. There are also researchers in Iceland. They did the same thing as you did. They also published normal values. Did you find the same thing, or were there any differences?
The values were the same. So initially, when we thought, when we devised a study, we had gone through a few papers, especially the one by James Beach in so he has spoken about the impact of the pigmentation, and we felt that because it is an Indian subject, there would be heavily pigmented fungi. So we can have significant differences. However, there was another study from the US by Jani et al., which was published in 2014, and they did not find any differences due to ethnicity, and they used the same machine. And we also found the same, absolutely the same values, and
Okay,
we felt
but
it was probably a regression to the mean. So
okay, so but there is one difference with the data from Iceland, and that concerns age, right? There was
okay.
something with lifetime, with age, with your data, right?
We found that with age, yes. So we found that with age, both the arteriolar and the venous saturations increased.
Hmm. Isn't this a little bit strange?
Absolutely, because this again did not make sense to us. We felt that the arteriolar saturation should remain the same,
Yeah.
whereas the venous saturations can increase because there is less tissue.
Hmm. Yeah, okay. So I think you sense already that I have some doubts about the whole oxygenation thing. So let's move then indeed to 105. So the table in chapter 7 on the retinitis.
Yes.
Well, if you look at the last column and you find something like smaller than 0.001 for the significance level, everybody is happy. Okay. So this is true for your arteriovenous difference.
Yes.
What could it mean that you find that significant difference in retinitis?
We again we didn't understand this completely because both the arteriolar and the venous difference went up. Like both the arteriolar and the venous values went up, and the AVSD also went up, and we just probably felt that the amount of tissue loss was less than the amount of constriction because even the diameters decreased. So we felt that the overall blood supply to the retina was decreasing more
Yeah.
than the amount of tissue that was lost. So there was actually more
Well,
demand
if we
than
if we
supply.
look if we again have a closer look at the table, so of course the arteriovenous difference is the result of subtracting arterios minus venous, right?
Yes. Yes.
And then you can simply see that the major factor that contributes to the larger arteriovenous difference is an incredibly and staggering arterial saturation of 102%. So
Yes,
the
sir.
venous saturation hardly changes, but the arterial saturation increases to an incredible value. So
Yes.
isn't this just an artifact?
That's what we very strongly believe, because anything, first of all, more than 100% is is not explained. The people who have made this machine have said that these are not absolute values and they are measured values, so it's a relative oxygen saturation and it is not absolute. But then still, the value increasing as compared to normals doesn't make sense, and we feel
Yeah,
that is
I think
because
my time
I'm sorry.
my time is up indeed. So I want to finish this, and I just want to say, I think you are not really measuring the oxygenation. You are measuring the reference and saying something about the reference, and that would explain that that retinitis pigmentosa does something to this value. But maybe we
yes.
can discuss this later on. I'm happy with your answers and give the word back to the prorector.
Thank you
Thank
very
you
much,
so much.
Professor Mess. You really started already a very lively discussion, which we really appreciate. And the opposition will be followed by Professor De Boer. He is affiliated with the Department of Biophotonics and Medical Imaging at the Free University in Amsterdam. Thank you for coming, and I would like to give you the word.
Thank you. Dear candidate, I would like to congratulate you on your thesis and the significant amount of work that you've done for this thesis. I've worked on developing oximetry measurements in the retina also. So I'm familiar with all the problems that you encounter, and therefore I read with much interest your chapter 12, where you expand on the different issues that are affecting your measurements. I also really like the idea of measuring the arteries around the optic nerve head with your argument that because they come from a central blood supply, the oxygenation in these arteries should be, so that's a good metric to test your models against. And also that in diseased states, probably the oxygenation in these arteries should be the same. So I know that it's very difficult to come up with absolute numbers, but this gives us something to hold on to. But then when I go through your list of problems that you encounter, and I will name a few, that is angle of gaze, the RNFL thickness, the media opacity and contrast, the central light reflex, and the background reflectivity. Is that a complete list, or would you like to add one to this list of problems?
Thank you so much for your comments, highly esteemed opponent. I think these are the major ones. Probably rattlesnaking, yeah.
Rattlesnaking is an observation. I don't think that's really, it's a consequence of a problem.
So one of them could be the effect of background pigmentation, which I think I have not mentioned here.
Background reflectivity. I consider that.
So even that I think I mentioned.
So this list is fairly complete in your opinion,
yes.
right? So what, in your opinion, is the biggest problem then in coming up with the right oxygenation levels in the arteries and the veins? Which do you consider your number one problem that has the biggest influence?
The RNFL.
RNFL. And why is that?
That is because, firstly, if we look at the algorithm, it takes the intensity on the side of the vessel as representative of what would happen of the tissue if the vessel was not there. But that is simply not true, because the RNFL on the side of the vessel is at least 100 to 150 microns thick, which is not present where the vessel is. So there is a huge discrepancy in that, and that the neighboring pixels cannot actually be representative of the light in. That is one point. Secondly, what we also found was there were areas where there was a lot of RNFL above the vessel. And this has the opposite effect. So if there is thicker RNFL on the side of the vessel, it decreases the measured saturation. But if there is more RNFL over the vessel, it increases the measured saturation.
Okay, I would like to add one thing, and that's the central light reflex. And why do you not consider that a major problem?
Yes, so if we actually look at how Oxymap chooses its points, it avoids the central area. So per vessel, it avoids the central area and chooses pixels on the sides. So I don't.
But the downside of that is that you also you have to use then a different vessel diameter, right? If you exclude the central portion, which has the central light reflex, then you're basically looking at a thinner vessel. So you should then correct for that, right?
Absolutely.
Yeah. But then the central light reflex also fluctuates among arteries and veins.
Yes.
So, and that is also strange. Why does one blood vessel have that central light reflex and the other one doesn't?
It's because of the wall thickness, probably.
That's your hypothesis.
Could be. I mean, that's what I can think about immediately.
Okay.
And probably also the location within the retina. Generally, arterioles are probably more superficial. So that too could probably have something. But then we know for a fact that the arterioles are thicker walls than the venules.
Okay. So I like the fact that you brought up the RNFL as your main problem, because let's say what would be your suggestion then to overcome this problem?
So if it is possible, I would like to have the RNFL thickness on the side and over the vessel throughout the entire length, but I know that's not possible.
Why is that not possible?
With the current technology, I mean, I don't know, probably with scanning, with the SLO-based devices, we might be able to get it through the entire length. But what we did was, for the RNFL study, we just measured RNFL at one point on the two sides of the vessel.
Yes.
So the pixel, like the entire vessel was 100 to 150 microns, but then it was just one point that we actually measured.
And with what technology did you do that?
We use the spectralis. So again, that was the SLO based thing. But
so that means So then you start to use structural information in your analysis, right? So I was hoping you would say that, but you need structural information on the retina. You cannot
Yes.
rely on just the color fundus
Yes.
photos. You need the structural information to feed your models to correct for, like, let's say, RNFL thickness and other things.
Yes.
And I mean, you tried that, but do you think that will be enough? So let's say, because you developed models, your model 4, or was it model 5? I think model 4, you model your RNFL thickness that's on top of the blood vessel,
Yes.
that's next to the blood vessel. But
Yes.
still, when you use that correction, then you calculate your variance in your venous oxygenation level, and you come out with a result that gives you a larger variation based on your model than when you did not apply the model.
Yes. And
So,
this, I think, is probably because we have not been able to factor in the light that probably gets when an X amount of light comes and the RNFL reflects it, it is, and if the RNFL reflects Y, then it is X minus Y that probably goes down. And that we have not taken into account. So we have not taken into account how much less light would go in.
okay,
Uh,
so that basically means that you have to come up with the scattering coefficients of the
Yes.
tissue, right? That is, you need complete characterization of the scattering coefficients of all the layers in the retina in
Yes.
order to model this propagation of the light better.
Yes.
And
Yes.
then when I look at your model 1, I know it's a simplistic model, but the way you model this is that the light enters the tissue, and on the way out it goes through the blood vessel.
Yes.
I assume that the reverse is also true, and that would result in the same amount. But going in through the blood vessel and coming out through the blood vessel is not part of your model. And isn't that also an important part of the signal that you get?
Yes. Yeah.
Do you have an idea how? And then is that a problem in your system, or is that more of an issue when you go to a confocal setup?
Yeah, no, I think I understand what you're saying. I think probably with a confocal setup, if I understand it right, then well, I think what we probably felt was there'll be very little light that probably comes back if it goes through the vessel and comes back through the vessel. So
So that's the reason.
I think Professor de Boer, sorry, I have to interrupt. We have to continue.
Okay.
I want to say this, and I thank you for the discussion. And we have to continue, and the opposition will be continued by Dr. Thelen. Dr. Thelen is affiliated with the Department of Ophthalmology at the Radboud UMC in Nijmegen. Welcome, and I'd like to give you the word.
Thank you, Mr. Chairman. Dear candidate, I want to congratulate you also with your thesis, your work you have done. I'm impressed of the comprehensiveness of your work, beginning from normal values and covering a lot of ophthalmologic pathology, as well as retinal pathology, as glaucoma and so on. So I liked it very much, and I'm also very enthusiastic about your work, because I have done a lot of work on reflectivity and absorption of the retina in the past also. So I liked it very much, and I'm also very enthusiastic about oximetry of the retina. Even though I had not the opportunity to do some own research on that up to now. But I would like to start with a question on chapter 7, because in Nijmegen we are dedicated to inherited retinal diseases, and you worked on retinitis pigmentosa and then on macular dystrophies in this chapter. And retinitis pigmentosa, what to focus on, is known to be caused by a lot of genes, more than 3,000 genetic mutations, about 70 genes. That's a lot. And the genetic overlap with other types of retinal macular dystrophies is enormous. So the same genes may cause different diseases. For example, the retinal metabolism is primarily affected by RPE65 gene, while the USH2H gene has impact on the ciliary function, just to mention 2 examples. So one may speculate that the primary involvement of a certain gene may have more or less impact on the oxygenation of the retina in that disease. So can you give some hints on whether your results were dependent on genetic course of the RP in your patients? And if you have no data about that, can you speculate on which mutation you would guess to have more impact on the oxygenation and in which way?
So, thanks a lot for your question, esteemed document. So, I think what you're basically saying is you are speaking about the genotype. What we are looking at is the phenotype, and we know that there is not a. I mean, there are certain mismatches sometimes between the genotype and the phenotype. Now, the phenotype where there is maximum alteration of the retinal reflectivity would cause artifacts, and the phenotype where there is maximum change in the retinal metabolism would cause a true change in the measured saturation values. So, so since this is just a speculation, where probably if a lot of photoreceptors are lost and there is very less demand for oxygen, ideally what we would expect is, if I mean in very advanced disease, we would expect the arteriolar saturations to not change.
So you have mainly, sorry that I interrupt, you have mainly measured the disease in a late stadium, I guess.
Yes,
and not
yes.
in an early stadium, because it would be interesting if to look at the retinal parts that are not yet involved in the late stadium. Have you any data about that? Can you speculate about that?
We did look at 2 different diseases. We have not really graded each disease as to whether it was early or late. We have just basically categorized that the disease was present. But
you have no data about the area, the fundus area that was involved, like 90%, 70% or so visible
no.
on the
So if we look
photographs.
at the 2 different subsets, one is the retinal dystrophies, that is the generalized ones, that is the RP, and the other one is the macular dystrophies. So the macula would involve a far less area, and generally the area where the dystrophy affects is in the macula, and we have not really chosen too many blood vessels in that. If you look at the area where we are choosing the blood vessels, it is around the optic disc. So,
Yes.
so we can probably speculate that the macular dystrophies would be representative of an earlier stage.
Yes, but if you look at the macula, it can also be involved in retinitis pigmentosa,
yes.
and there can be a cystic macular edema in the macula of retinitis pigmentosa patients. And
Yes.
a recent study of Bojanova and co-workers published in Eye showed that the RP patients had significant higher blood oxygen when CME was present. So what did you observe in your study group, and could you speculate the causes on changes in the arteriovenous oxygenation in CME cases?
If I understand your question right, we did not look at the systemic values. We just looked at what the values were inside the eye. And
yeah, I understand, but I'm talking about the cystoid macular edema in RP patients, if or not present. So were there any differences in oxygenation, and why should that be?
I don't think any of the cases which were included had cystoid macular edema.
So you did OCT, so you checked that?
Yes, yes.
Okay.
I don't think there was cystoid macular edema in any.
So your data are only about non-CME cases then?
That's what I think.
And what do you think, why did CME cases have a higher blood oxygen in this other study? What do you think?
It had higher,
Yes.
I'm not familiar with the study. It had higher blood oxygenation systemically.
Yes.
So what I can speculate is that there is some inflammation that is happening, which is why there is a CME, because generally the CME happens because of a breakdown of the blood retina barrier. It means that fluid is leaking from the vessels into an area where it is not supposed to be leaking into. And this is generally a surrogate for some inflammation that is happening. And when there is an underlying inflammation, it can.
But don't you think that's because a macula of CME does have less absorption of oxygen, and because it's less functioning or something like that? I would say that that's the reason why the oxygenation is less.
It could be,
Maybe.
yes.
Okay, I would like, if I have some time left, I would like to
I'm
go
sorry,
to
you don't.
chapter 4.
No. Hello.
Yeah.
Well, there is no time left. I'm sorry.
No time left. Okay,
And
then I give the word back
we
to
have
you.
switch to we have
Chairman.
three more opponents, and I really like to give all of them the opportunity to discuss. So thank you very much, Dr. Taylor, and we will continue with Professor Lambert. He is appointed as professor in precision medicine and also a member of the assessment committee, and I'd like to give him the word.
Yes, thank you, Mr. the Prorector. Mr. Promovendus, I would like to congratulate for the excellent work. You have a lot of patience in your studies. You do some modeling studies. So you have shown your capacity to do research. I would like also to congratulate the promotion team. So I have a background of a radiation oncologist, and we are used to work with machines, and we have learned not to trust them blindly. So for example, when we receive a machine, we do commissioning, testing, acceptance, and maintenance. So I just wonder, have you done that for your machine Oxymap, or how reliable is your machine? Is there any technical variability?
Thank you so much for your comments, highly esteemed opponent. So we did not do a very formal sort of a testing like what you suggested, but then what we did was we did look at a few normals, we looked at a few disease, and we felt there was a difference, and we also went through published literature. And the published literature at that time in 2013, 2014 was overwhelmingly speaking about the benefits of this, where they were speaking about the high standard deviation, but then they were speaking about significant differences between the diseases
So
and the
you feel
normals.
that there is no significant technical variability between the machine and the same machine. For example, I'll give you a concrete example. If you start to make an analysis in the morning at 8 o'clock and you finish at 7 o'clock p.m., are the measurements the same? Have you done some retests on a sort of a phantom or something to confirm that, or has been done? Has it published somewhere?
As far as I'm aware, I have not read any article like that, and we also did not do any such study. Probably I'll keep that in mind the next time. I'll try to be more thorough with the preparation before we embark on
Okay.
this.
Right. Another question, again, in analogy with my specialty. We also tend to use phantom to have sometime to try to generate absolute value. I've seen that the inventors of this method also try to use similar phantom.
Yes.
Is there anything like a phantom or an attempt to simulate an eye to eventually also be able to have the gold standard, the real absolute value rather than relative? Are you aware of any work like that? Have you tried to do that?
I have read a few articles which have spoken about a phantom like this, but I have personally not seen one, or I've personally not had the privilege to use one. So
Okay. Do you think that would be useful to try to work on a phantom of the eye
absolutely.
All right. Okay. Then I want to know to have a questions about smoking status. Is that something that you recorded in your patients, whether they were a smoker or not? And do you think it could have an influence on the measurement?
Absolutely. So none of the subjects in the entire thesis had a history of smoking. So and so much so that even a history of caffeine intake 2 hours before we did not rule the patients in.
Do you think
So
it would have an impact eventually on the oximetric measurements?
it could. That's what the literature
And
said.
what would be the mechanism of that?
Generally, nicotine or caffeine would, on one hand, increase the metabolism, but on the other hand, it can also cause vasospasm.
All right. And what about carboxyhemoglobin? You know that
Yes.
smokers, especially heavy smokers, they can have up to 10% carboxyhemoglobin.
Yes.
So I saw your formula to look at saturations. So do you think that we should add an extra element, variables in your formula to calculate saturation if you have heavy smokers?
Yes, absolutely, because the oxyhemoglobin dissociation curve would be shifted to the left.
Yeah.
with carbaminohemoglobin, because you would have more affinity of oxygen to that, and that would interfere with the release of oxygen into the tissue, and especially it can affect the arteriovenous saturation difference. Not so much the arterial difference, but the AVSD can be adversely affected because of this.
Okay. Also you mentioned the fundus pigmentation in your thesis, and you said that for each population you would need to try to get sort of normative database, something you have
Yes.
done in chapter 2.
Yes.
So suppose this machine examination would be done in a multiracial clinic. How would you deal with that? Would you have to have sort of several reference, or would you have to generate a sort of a reference for each patient? How would you deal with a multiracial population then, if you think that pigmentations has a significant impact?
So the recommendation from the company is that ideally we should do the calibration for each race. That is, assume based on the paper by Schweitzer in I think 1999, where they did describe, where they used about 76 different wavelengths, and they did describe what the normal was, and they said that 92.2% was the normal in the arterioles and 57 was the normal in venules. They expect us for each, I mean, to take about 20-30 normals and do the calibration in them for each race.
Okay, right.
So this is a simple linear regression where there is x is equal to a plus b into c. So we need to get those constants.
Yeah, but that's not so necessarily so easy. If you go in the US, for example, where you would have different mixed
Yes.
race, and how would you see that in practice then?
So there was one study in 2014, which was published from the US, which had about 60 subjects. And I think they had 15, I mean, 4 different ethnic groups, probably 15 in each group. And they didn't find any significant differences based on race.
Ah, okay. So it's not necessary then, or is it?
Yes, so I don't think it is necessary. So one very important thing was this algorithm on which this machine is based was based on the paper by Beach et al., which was there in 1999. But when they finally made this machine, they used the beam splitter principle from that study, but they did not use a very important principle, that was the EVR, or the extravascular reflectance, that compensates for fundus pigmentation. So they have done away with that model for this machine. They have just used a simple linear regression, and this was
good. Thank you. Last question.
I'm sorry. Sorry, Professor. I also have to interrupt you. Your time is also finished, and we still have 2 more opponents to go. So I would like to thank you too. Sorry, and I would like to I would continue that with Professor Beckers. She was also a member of your assessment committee and is appointed as professor of ophthalmology. And I'd also like to give her the word.
Thank you, Mr. Chairman. Dear candidates, firstly, like the others today, I would like to congratulate you with the enormous effort that you have done to do the research that you did in this thesis. It needs a lot of courage and a lot of persistence. However, working with the new method that you presented offers possibility for the future, albeit that problems like artifacts still have to be overcome, as very apparent from the discussion today. I am a glaucoma surgeon, and as such, I'm especially interested in the additional value of retinal oximetry, what this may offer for glaucoma research and ultimately the glaucoma clinic. As you know, perhaps the pathophysiology of glaucoma is still extremely complex and poorly understood. We do know, however, that abnormal blood flow as a result of impaired autoregulation does play a role, especially in normal pressure glaucoma. Unstable blood flow and hence unstable oxygen supply leads to oxidative stress and progression of optic neuropathy. Vasospasm and endothelial dysfunction also seem to play a role. So that's a lot of things that might be happening. And in your thesis, I do not wonder that you seem to struggle with the findings in glaucoma patients, as mentioned earlier today. However, except from the fact that artifacts may play a role, there are still many differences between our glaucoma patients in the disease mechanism. We have beginning versus end stage, high pressures versus low pressure, genetic factors, etc., etc. And in the past, many methods have been used to study ocular blood flow. And however, only OCT has really made it to the clinic. And perhaps OCT angiography is probably now the most promising for the near future. I'd like to ask you a few questions on this. If you want to do further studies on glaucoma, which patients, which selection would you like to make? Which are the most promising for the future? Perhaps you can first comment on that.
Thank you very much for your comments, highly esteemed Robin. So the selection actually, I mean, initially I would like always choose somebody who has slightly more advanced disease, but who has the pressures controlled. The reason for this is because the intraocular pressure will alter the ocular perfusion pressure. And we know that the ocular perfusion pressure also can affect oximetry and it can affect flow. One more point that I would like to make is that oximetry is a percentage and it is a static measurement. It is at a single time point. But what I would ideally like to do is incorporate blood flow and have the actual volume or how much oxygen is delivered per minute to the eye, which is probably, a more important thing to look at. So oxygen percentage is is just one. I mean, it's just looking at one dimension of the image, and it doesn't give us the entire picture.
How
So
do you want
especially,
to look at blood flow, and how would you like to combine it with your method?
so so one is how much blood flow is there, that is the flow volume per minute, and then probably multiply that by the arteriovenous saturation difference, and then understand how much oxygen is being delivered to the retina per minute, or how much oxygen is being consumed by the retina per minute, and that would probably give us a better picture.
Yes, and if you want to study like this, you already mentioned your thesis, you probably lead a large cohort of patients that you would like to follow for some time. So
Yes.
to do a successful study, how would you see this this happening? How many patients would you like to include? For how many time do you think you would need to follow them up to get any significant results?
So I think we should at least follow them up for 3 to 4 visits. So probably for a year, 3 months apart, and probably at least about 30, 40 patients. About a number of 30 would be a safe number.
That seems very low to me.
Initially for the pilot, because especially with this, with the technology and with the considerable doubt with the artifacts that we have, I think um, because I think this initial number, when we compare their visits with each other, we'll at least know how much difference there is. Because if we look at the published literature, they've actually said that in normal subjects, within the same day, the same segment has a standard deviation of 3.2%, which is a very large number. So um, so I think before we actually go on to the longitudinal studies, we should first iron out the artifacts before that.
Yes, I agree with that. But if you mention the artifacts, what are really the chances that you think that you can bring this new device to the clinic? Because it seems there's still a lot of work to be done, and correcting
Yes.
for artifacts, additional modeling. And I don't think you give me a very clear answer on what kind of studies that would be needed. For example, do you think that artificial intelligence and the outcome of this might help you in making progress?
I don't really think artificial intelligence would help. I think we need like I think what we discussed, we need more structural information. We need some more data on what is happening in the retina, because in the normal subjects we can probably assume that these are parameters which would be constant for everybody, but especially in disease, even one parameter changing, we know that it can adversely affect the measured reflectance, and
Yes,
hence we need a
yes, very true.
comprehensive measurement thing where we are incorporating, where we are taking into consideration structural alterations in the retina, and where we are uh, either incorporating a correction for it. Like for example, when you measure the IOP, you do take into consideration the central corneal thickness and you do correct for it.
Yeah, yes,
So
true. This says, if I
similarly
may
here,
interrupt you, this you are telling me that to get a prognosis, perhaps on progression of patients.
I'm sorry. I also, before
Yes.
before you start the question, I have to interrupt because your time is finished already too.
Yes. Yes.
And I have to.
Thank you.
Thank you very
I
much.
give you back the word.
Because I noticed. So we have to move to the last opponent of yours, and we move to Professor Maassen. Professor Maassen is involved in the Department of Cardiothoracic Surgery, and I'd like to give him the word too to discuss with you. Professor Maassen. You have to unmute.
Thank you, Mr. Prorector, and dear candidates. Congratulations with your work. I really think that you wrote a reference book on this subject. And I'm a little bit overwhelmed, and I must apologize that I'm not an ophthalmologist, that I'm a cardiac surgeon. But also we as cardiac surgeons have to know about oximetry, because oximetry is a very important during our during surgery. When the patient is on a heart-lung machine, then it's actually the only way how we can take care of the brain and see whether the brain gets enough oxygen or not. So for us, it's very important. But a huge difference, I think, between the way we use it and you use it is that we have always continuous measurements. And your measurement, as you pointed out earlier, is a static measurement. So I think that a number of difficulties you experience, we don't have because we have this continuous measurement. And that's also slightly related to my first question, that is about the way you validated your algorithm when you compared it to the manual assessment. You used the Bland-Altman plot to compare these two methods. And I think from a statistical point of view, the results are perfect. However, if you look at the differences in percent from the average values, then the limits of agreements reach 6% and lower close to 10%. Do you think that from a clinical perspective, these values are acceptable?
I thank you for your question, highly esteemed opponent. So are you referring to the Bland-Altman plots on page number 45, to just clarify?
I'm sorry?
Are you referring to the Bland-Altman plots on page number 45?
Yes, in chapter 3. Let's see. It's in the figure 6.
46?
You have the lower limits,
yeah,
and the higher limits.
Right. So actually, I personally believe that that because of the artifacts that are there, the averaging would lead to influence by extreme values. So there can be outliers which are also influencing these readings. But in the automatic analysis, we have chosen the bimodal plots. This is probably a more accurate estimation because we are looking at that one saturation that occurs most frequently. So actually this might be a more accurate representation, and especially when, if you look at the earlier images of the rattlesnaking artifacts and all those things would be probably eliminated with the bimodal distribution, where we're just choosing the one that occurred most frequently.
Yeah, the reason why I ask is that, to my knowledge, an important part of the Bland-Altman method is to test the repeatability. If there is not really a gold standard, and I think that the manual assessment is not really a gold standard, yes, then repeatability would be very important. Did you test that, or?
No, we didn't look for the repeatability in the study. No, we didn't.
Okay. Then I have another question on chapter 2, and that's about the effect on age.
Yes.
And yeah, you say in page 22 that there was an increase in arteriolar and venous saturation with age, and that the AV difference did not show a significant change.
Yes.
And then in the diagram, we see significant p-values, but very low r values.
Yes.
What is your interpretation of that?
So so I think the R values are low because the difference in age, it contributes only to a very small percentage of the change, and it is actually said that if we divide a population and if we have probably high enough numbers, then we are going to get a significant p-value even for slight differences. So I mean, the thing is, age did not significantly, did not play a very major role, but the two groups had a statistically significant difference when we compared the means.
Yeah, yeah.
But I wouldn't. I mean, like the only thing that, again, like if you.
Mr. Moore, you can finish your answer if you want.
Okay, so if we actually look at that, what we did see was there would be a few young subjects with high saturation values, and there would be a few older subjects with low saturation values. So it wasn't an absolutely golden rule that as you age, the saturations increase. It was just a general trend that just probably would contribute to about 20 to 30% of the change, not more. So it wasn't a very strong trend. It was a significant trend, but it wasn't a very strong trend.
Thank you very much. Mohan. Mr. Mohan, the time appointed for defending your thesis has now passed. The degree committee will now withdraw online to discuss not so much the quality of your thesis that has already been approved, but moreover, the way you have defended your thesis this afternoon. I request that you and your company await online the results of our deliberation, and we will return in about 10 minutes. Thank you very much.
Thank you.
look. Yes, everybody's present. Good. Mr. Mohan, the degree committee here present, online, of course, has assessed the quality of your thesis, but in particular the way you have defended your thesis this afternoon. And in view of a positive verdict and taken into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Webers, as your first promoter, is authorized to confer upon you this academic distinction in accordance with Dutch university custom. And therefore, I would like to invite Professor Webers now to take the floor. Professor Webers.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, sir, I do.
By the authority vested in us by law and in conformity with the decision of the committee here present online, I hereby confer upon you, Ashwin Mohan, the degree of doctor and grant you all rights attached by it by custom and law. As evidence of this, you will soon receive the degree certificate signed by the rector, the secretary, and the supervisor, affixed with the official seal of the university shown by the beadle.
And I like to give the word to Professor Webers because he likes to give a laudatio. Professor Webers, you can continue.
Dear Dr. Ashwin Mohan, it gives me great pleasure to address you first after achieving your doctoral degree. I had no idea how our cooperation would evolve when I received a request to be, as you call it, your guide for your PhD course. Today, again, and like many colleagues, you have proven not only to be a true and rightful member of the scientific community, but also that you are a representative of the young and bright Indian generation that makes your country so proud. Writing a thesis is teamwork, and in your case, 2 team members should be mentioned. The first one is Dr. Rohit Shetty, who has made this work possible from the Bangalore side. Dear Rohit, thank you again for all the efforts you made to continue the partnership we have. I'm looking forward to the many numbers of students that will be guided by you, your team, and us. The second team member, of course, is Dr. Tos Berenschot. You have been to our clinic several times to perform the necessary complex analysis on the data, and Tos has been very helpful to you. And therefore, it's much more appropriate that he will tell us how he has experienced working together with you instead of me. Therefore, I now would like to give Dr. Tos Berenschot, as one of your daily guides in this PhD track and adventure, the opportunity to also address you. Tos.
Dear Dr. Mohan, dear Ashwin, it's a privilege to be one of the first to congratulate you on your PhD. Obviously, we all regret that because of COVID-19, and I have seen the numbers again this morning about the situation in India, we all regret that we could not meet live and had a virtual meeting instead of an actual one. But I think your defense was real, far from virtual. You did very well, and your diploma is very well deserved. And as it will be clear in the next few minutes in my talk, it has been a long and interesting journey. Our collaboration goes way back to March 2015, when we first met during my visits to the National Institute of Mental Health and Neuroscience and the Narayana Nethralaya Eye Hospital in Bangalore. Dr. Rohit Shetty and Dr. Shyam Vasudhave Rao had organized a meeting with several possible PhD candidates. And with some good cups of coffee, I sat down the whole afternoon to discuss their projects. And I remember vividly still your presenting work on oximetry and me expressing my questions and doubts on the saturations way above 100% that I've noticed in several papers published by other groups. Everybody seemed to take this obviously impossible value for granted, but as a real scientist, you were not deterred by this. On the contrary, as you mentioned in your acknowledgements, this discussion rekindled the curiosity and inquisitiveness in you. And indeed, you did not waste time. Then your first email thereafter, dated March 12, 2015, and I guess it's likely the same day in the evening, you already presented a possible table of contents of your thesis to be included, already some graphs, like the modeling graphs shown in your layman talk today. Obviously not that pretty, but at least the ideas already came up. Fortunately, you both went to the annual meeting of the Association of Research and Vision in Ophthalmology only 2 months later in Colorado, May 2015, and here we had ample time to meet and discuss oximetry, its promises, but also its pitfalls and possible ways to tackle these pitfalls. Well, as you already mentioned, the idea to determine retinal oxygen saturation using blood absorption was already proposed way back in 1959 by Hickam and collaborators. Francois Delory, an expert in this field, in 1988 used 3 wavelengths to determine this saturation, but the first to use the full wavelength region covering 76, as you also mentioned, were Schweizers and co-workers in Jena, the former East Germany, and it allowed them to get, I guess, reliable individual estimates in their 28 Caucasian subjects that showed large individual differences indeed. Despite this huge range, their mean value was used as the one and only value possible for the saturation, determined by only 2 wavelengths by another group in Iceland that eventually commercialized this technique, and that's the one machine you used. And not only they used this one and only value for all the subjects, but also keep in mind, these were most probably very blue-eyed, healthy subjects from Iceland only, so not the one from Eastern Germany. And doing this way, they came up with a rather simple algorithm that from now on has been used in different studies, different populations, like from India with rather dark-eyed subjects and different diseases. And as you all can imagine, this very probably will and indeed leads to the pitfalls of which you mentioned a few and which came by during the discussion the last hour. So we set out to tackle them, and we had a number of promising ideas that we started to work on, but unfortunately, in practice, these approaches turned out not to lead to the solutions we've envisioned. Although, for instance, we added extra information from optical coherence tomography images, so structural information, there still remained unknowns that we were unable to quantify. Nevertheless, I think it's only fair to say that we learned a lot, and I'm confident that the hyperspectral imaging, which yet another bright scholar, Shui Zhang, is working on, will in the end enable us to get more reliable individual estimates, not only in the healthy, but also in patients with retinal diseases. Obviously, regular Skype meetings are fine and they work all right, but once in a while, one really needs to sit down at the kitchen table to discuss science with paper and pencil. So we decided to meet in Maastricht. First, it took some time before we actually met, since for several reasons, possible dates were postponed a couple of times, but eventually you visit our university eye clinic October 2017, where we discussed over and over the different models for pathways of light at and near retinal vessels that would allow better saturation estimates. And although at the end we did not yet decide upon the final one, we learned a lot. April 2018, you again visited us to continue this discussion. And during this vision, I remember strolling down the old town. We went to the marketplace and finally ended up in the Vogelsruis, where we had our local cheese, the Romadoux, with Dutch roggebrood, a taste that is not yet, I guess, familiar with in India. I really appreciated being in Bangalore that you introduced me to the local food, so I thought it to be a good idea to let you taste some of ours. Hope you enjoy the taste of it. That for sure is much better than its scent. Dear Ashwin, We started our work March 2015, and here you are, April 2021. Research takes time. Sometimes one takes paths that lead nowhere and only take time. On the other hand, sometimes they lead to new ideas and unexplored areas, which takes time to study. Time was, however, never an issue when preparing manuscripts. Whenever I propose some modifications, a new analysis, different approach, whatever, you always surprised if there is not any time difference between Maastricht and Bangalore. It was a pleasure to work with you in this way. In the end, what really did take time was waiting for reviewers to comment on the papers we uploaded. In the Netherlands, to obtain a PhD very often is a job on its own. You managed to combine it with your work as a vitro-retinal surgeon, first in Bangalore in the group of Rohit Shetty, where it all started, but thereafter in Susila Nitralia, and eventually in the Chaitanya Eye Hospital and Research Institute in Coimbatore, where you in the lead of all the research. And also, as can be seen at the back of your thesis, there have been changes in your peripheral eyes as well, which I guess did alter your nights at least for some time as well. And in light of all this, your thesis is all the more impressive, I think. I'm almost finished, but before coming to an end, I like, as Professor Webers did, also like to thank your co-guy, Dr. Rohit Shetty, who introduced you to me about 6 years ago, and who, like you, is not allowed to be here today, unfortunately. I know he's always been a mentor for you as well for many scholars that we guide, and I hope will be in future. Finally, although in a sense this is the end of a journey, it's also the start of a new one. We have agreed to stay in touch and start new challenging research projects the upcoming years. And indeed, you are the right candidate for this. On the one hand, an ophthalmologist with an eye for questions and uncertainties that still exist from a medical point and from a patient's perspective. And on the other hand, having the knowledge and experience to initiate research to answer them gained in the past years. And of course, we will visit each other to celebrate in person this achievement, but also because in addition to ophthalmology, there are also other aspects that are more than worth investigation, like culture and fruit from India and the Netherlands. Dear Ashwin, it has been a real pleasure to guide and work with you over the past 6 years, and I look forward to many more to come. Take care, keep healthy, and hope to meet soon. I give the word back to the prorector.
Thank you very much. And I think we all can unmute and we give a little applause to the candidate. Okay. And this has also enabled us to make some screenshots from all of you, which we can give later to the candidate. Dear Dr. Mohan, I think it feels good now that I can address you with the correct title, which you also can use now in your future career. Also, on behalf of the Board of Deans of our university, I would like to congratulate you officially with this new title. In my congratulation also will be, of course, your promotion team. And I'll also look particularly to Dr. Shetty and Dr. Berenschot. Dr. Shetty, we heard a lot over the last almost 8 years about the work you are doing together with the ophthalmology department here in Maastricht together, and the excellent collaboration which we have established between India, the Bangalore region, and Maastricht University. And I thank you for these all these endeavors. I also would like to thank all the members of the Corona who took the time to have today, which I would call, and I do a lot of thesis defenses at the moment, we had today some lively discussions, I would say. I had to do a lot of interruptions, and this is always a good point, which means that people are getting enthusiastic to discuss with the candidate. I would like to say, Dr. Mohan, I hope you enjoyed the thesis defense by yourself. Of course, we would love to have you here live in Maastricht with your friends, with your family. But I still hope that also this event online has an idea that you could, what we can say, shine today, to put it a little bit in the perception of an ophthalmologist. Okay. Enjoy your career and thank you very much. And by saying this, I will officially close now this ceremony. Thank you very much.
Thank you, sir.
And I think the recording will be stopped now. Thank you very much.